By now we've learned how to write the expression for the equilibrium constant and what it means to be at equilibrium, but what we haven't really learned is how to tell if a reaction is at equilibrium or not. Now, the very first time we run a reaction, what we can do is we can measure the concentration of all my things as a function of time. So we would imagine that my reactants will decrease over time and then plateau. My products will increase over time and again then plateau. So we have reactants and products. And we can just measure that concentration over time, and once we reach a point after which those concentrations don't change anymore, once we've hit that plateau, that's how we know we're at equilibrium. But in reality, it takes a lot of effort to keep watching this over time, especially if you have a very long reaction, a reaction that takes hours to get to equilibrium. So it would be nice if we had a quick way to just look at our reaction and tell, has it reached equilibrium yet, without having to make this type of graph. And the good news is we do. The tool we use is what's called the reaction quotient, which we abbreviate with this letter Q. If we notice, Q looks exactly like K. It's just this ratio of products over reactants. The difference is that K applies at equilibrium and Q applies at any other point. So Q is just this general ratio of products over reactants. If we know K for a reaction, let's say we had already measured this and we knew that K was equal to 100. What we could do is we could, at any given point in the reaction, measure all the concentrations of reactants and products and plug it into this equation and see what we got. If Q matches K, then we know we're at equilibrium. That ratio is equal to 100. We're equal to the equilibrium constant. We must be good to go. But let's say Q does not match K. That means I don't yet have that ideal ratio of products over reactants, so I must not be at equilibrium yet. And I can not only determine that, but I can actually figure out, do I need to make more reactants or do I need to make more products to get to equilibrium? So we have basically two scenarios. Q can be too small. For instance, let's say Q here was 1. In that case, we just need to think about the form of this equation. So Q is smaller than K. And if we look at the ratio, Q is always products over reactants. If Q is too small, then this piece up here must be too small. That means I don't have enough products and I need to make more products in order to get to equilibrium, because my reaction is always trying to get to equilibrium. So if Q is too small, number on top is too small, I don't have enough products, so I'm going to make more products to get to equilibrium. If on the other hand, Q is too big. Let's say Q was 10,000, whereas K was 100. In that case, Q is too big, and if I look at this ratio again, products over reactants, if Q is too big, that means my products are too big. I have too many of them. So I need to make this piece on bottom larger to reduce my number down to what it should be. So if Q is too big, I have too many products, so my reaction is going to make more reactants to get to equilibrium. And again, if Q is equal to K, life is good. We're already at equilibrium. So let's look at an example. Let's say we had this reaction right here, and previously we had measured K to be this number. Now we're running the reaction again. It's been going for a while, and we want to know if we've reached equilibrium yet. So we measure the pressures of everything involved, and we see that we currently have 0.112 atmospheres of hydrogen, 0.055 atmospheres of sulfur, and 0.445 atmospheres of H2S. Is the reaction mixture at equilibrium? Anytime we see this question, we say, okay, what I need to do is check Q and see if Q is equal to K. So first I'm going to write that general expression. So on top, I'm going to have H2 squared, S2. And I'm not using my brackets because these are pressures. I should be writing in my P's, but it's kind of hard to do that on my tablet, so I'm cheating a little bit. So I have H2 squared, S2. And then on the bottom, I have H2S, also squared. Don't forget about your coefficients there. So I have the expression, and now I just need to plug in my values. So H2 is 0.112 because squared, because Q is also unitless. We don't have to worry about my units. S2 is 0.055. So 5, there we go. And H2S is 0.445. 5. Oh, squared. Don't forget about your exponents. So we just plug that guy into my calculator and we see that Q is equal to 3.48 times 10 to the negative third. So we calculate Q and now we compare it to K. So we see that K here is 2.4 times 10 to the negative 4, whereas Q is times 10 to the negative 3. So that means Q is bigger than K. So if we think about my expression, Q is too big. This part on top is too big. I must have too many products. So I'm not at equilibrium because the numbers don't match. So the answer to my first question is no, I'm not at equilibrium. In what direction will the reaction proceed? Well, if I have too many products, which I can tell because my number is too big, then it must need to go backwards and proceed towards reactants. Now, some people are very visual. So another way to do this is kind of to put this on a number line where you put K in the middle. So K is right here. I'm not going to try and write the number in because it's kind of long. And we see, okay, Q is bigger than K, so Q would be past K on the number line. So in order to get to K, because we're always trying to get to equilibrium, I would have to go to the left or towards the reactant side. So you can think about it either way. If Q is too big, the piece on top is too big, I have too many products, I need to go to reactants. Or put it on your number line, think about the direction you need to go to get to K, and that'll tell you what direction you need to go in your reaction. Thanks to Nate for showing me this trick. I love it. It's fantastic. I always love it when the student can show me something.